Hello friends, welcome to my YouTube channel Aviator Updates. If you don't know me, I'm Rakesh Negi and I'm an aviation enthusiast. In today's session, I'm going to discuss about what is VLS and what is VAPP or VAPP. Okay, so what is VLS and what is VAPP? Okay, so VLS, this represents the lowest or minimum selectable speed. Lowest or minimum selectable speed. And what is this VAPP? This is your final approach speed. So friends, let's discuss about these speeds in detail. So let us begin with VLS. So what is the purpose of VLS? The purpose of VLS is to provide an appropriate margin to the stall speed. Okay, so it's to provide appropriate margin to the stall speed. Okay, so this is the purpose of VLS. Purpose of final approach speed, it is in the name itself. So during the approach, okay, the pilot should maintain a stabilized approach, and that is by maintaining the approach speed. Okay, next, as a general rule, the pilot should never select a speed which will be below this lowest or minimum selectable speed. Okay friends, now friends, let us understand where you can see this VLS and VAPP, that is the final approach speed. Okay, so for this, let me consider Airbus A320 aircraft. So in this aircraft cockpit, there is a display by the name PFD. Okay, primary flight display. Suppose this is your primary flight display, which is a part of the EFIS, which is electronic flight instrument system. So on this PFD, on the speed scale, suppose this is the speed scale. Okay, so on this speed scale, suppose there are speeds randomly writing. Suppose this is 180, then 70, then 60, then 50, then 40, then 30, then 120. Okay, so suppose this is the speed scale of the PFD. So on this speed scale, we get the VLS indication. How do we get? In terms of an amber strip. So I don't have amber color marker, friends, so I'm using blue ink to show you the strip which shows you the VLS. Okay, suppose instead of amber color, I'm using this blue ink. Okay, so consider this blue ink as the amber color. So suppose this is the amber strip. Okay, this line which I have drawn. Then in this amber strip, we have another amber strip which will look like this. Blue, then white, then blue, then white, blue, and then white. Okay, so this is another strip, and then we have a red color strip here. Okay friends, so the top part of this strip, which is considered as amber strip, which will be shown in amber color, though here in this board it's blue in color. So the top part of this amber strip is called as the VLS. Okay friends, this is your VLS. Next, of this amber white color scale, this is your alpha prot speed. Okay, alpha prot speed, it is that speed at which your aircraft is at alpha prot. Okay, next, the top part of this red color. Okay, can you see this red color strip? The top part of this is your alpha max speed. So this represents your alpha max speed. Okay friends, so we are concerned more with the VLS here. So on the PFD, VLS indication is indicated in this way, which is at the top part of this amber strip. Okay, so that's how you identify VLS. Next, VLS can also be seen on the MCDU, and you know friends, what is MCDU? MCDU is multi-purpose control and display unit. There are two MCDUs in the cockpit of Airbus A320 mounted on the center pedestal. So I'm just drawing one of the MCDU. Now in the MCDU also there are so many pages. So what you need to do is on the keyboard of the MCDU you need to press the performance key. Okay, there is a key by the name PERF, perf or performance. If you press that key, then a particular page will open. Okay, so suppose the aircraft This is in the approach phase, and we have selected the approach page by selecting the performance key. So this is the approach page of MCDU. On top it will be written in APPR in white color. Okay, so this is a MCDU. Which page? Performance page. I'm writing here PRF. Okay, so here on this approach page, what all data do we have and how do we see the VLS and VAPP in this page? Okay, so on this page what you have is you have QNH, okay, then you have temperature, then what else you have? Magnetic wind. Okay, so this magnetic wind, so this is a field where you have to enter the data related to the wind which is reported by the tower. So whatever information the pilot gets from the tower about the wind is entered in this column, okay, or this field. Next we have transition flight level. Whatever would be the transition flight level will be written here. Next we have VAPP, okay, which is this one, final approach speed. It is shown here. This VAPP which I am telling you will appear here in blue color. Okay, it's in knots and it is calculated by the FMGC. Okay friends, moral of the story, FMGC calculates the VAPP and shows it here. Pilot can also modify the VAPP as and when applicable. Okay, so that we'll discuss after some time. What else do we get on this page, friends? So here in the end we have previous, phase, and rest. What we have here, we have the flap retraction speeds. So some speed will be written here, okay, flap and some speed. Suppose the speed is 145. Okay, next we have slat retraction speed here, slat retraction, that is the S speed we call. Let's suppose it's 186, and then we have the green dot speed, okay, which is written here. So by means of the letter O, okay, suppose the green dot speed is 202. Next, what else do we have on this approach page? Here you can get the final, whatever is the runway you're using, suppose ILS 2728, whatsoever is doing, is it will be written here in blue color. Next we have the MDA, whatever MDA is there you have entered, it will be shown here in blue color. Next radio or DH, okay, that value is shown here in this field. Okay, so this is the MCDU, and here we have the config, whatever config, like config 3 or full, will be written here in blue color. Okay, whatever you are preferring for. Next here it will be written as next phase. So this is the approach page of your MCDU. So on this approach page, the most important thing which we are about to discuss is VLS. So VLS will be written here, VLS. So VLS is written in this area in blue color, and VAPP as discussed will appear here in blue color. Okay friends. So now what we have discussed is where is the VLS indicated. VLS is indicated on PFD and on the MCDU as well, right? On the PFD, where is it indicated? It is indicated by means of an amber strip. The top of the amber strip indicates the VLS, okay, as we have seen. Next, on the MCDU, where is the VLS indicated? It's indicated on the MCDU performance approach page. You can see it here. This is the VLS. And what about the final approach speed? You can see it here. So that's what we have discussed till now. Next friends, let us learn how VLS and VAPP are computed. Okay, how VLS and VAPP are computed. So to understand this, okay, let us start. Let's first discuss about VLS. So regarding VLS on the PFD, okay friends, on PFD, how is the VLS computed? So whatever VLS you see on the PFD, it is computed by a computer which is called as FAC, FAC. FAC stands for Flight Augmentation Computer. There are two FACs in Airbus A320 aircraft. Okay, if one fails, we have the other one. So FAC can compute your VLS. How does it compute VLS? The answer is FAC computes VLS by taking into account the aerodynamic data, gross weight and CG. So now you should know that friends, the accuracy with which CG and gross weight are computed by FAC, okay, that will give you the accuracy of the VLS calculated by the FAC. Okay, hence moral of the story, VLS is computed by FAC based on the aerodynamic data, cross weight and CG. Okay, next, as discussed earlier, VLS is also indicated on MCDU. So from where is this VLS appearing on this MCDU? This VLS which appears on this MCDU, note that friends, it is computed by the FMGC. Okay, how does the FMGC compute? Okay, how does the flight management FM of the FMGC compute this? Okay, it computes VLS by taking into account the pilot's input. So if suppose the pilot has entered wrong inputs, then the VLS computed by FMGC also will be wrong. Okay, suppose the VLS which is computed by FMGC based on the pilot's input is 131 knots. Okay, so it is indicated here on the MCDU performance approach page. Okay, so based on the VLS value, the VAPP is calculated. Okay, so I mean to say, how is the VAPP calculated? VAPP is also computed or calculated by FMGC. How is it calculating? So there is a formula for this. So I'll explain it here. So FMGC uses this formula, VAPP is equal to VLS plus 5 knots. Okay, so this is the formula which FMGC uses as a reference to calculate the VAPP. But in addition to this, there is also one more case. Okay, it is VLS plus 5 knots, or FMGC also considers this VLS plus 1/3 of headwind component. Okay, so 1/3 of headwind component. Which headwind component is this? The tower reported wind. Okay, so whatever is the tower reported wind, 1/3 of that wind is added to VLS to get the VAPP. Okay, and this is the calculation which is used by FMGC to calculate the VAPP. Okay, so let's take an example. Suppose tower has reported the winds as 0.75 degrees and 0.8 knots. So in this case, 0.8 is the speed of the wind, right? So in this case, as per this winds, how much will be the approach speed which FMGC will calculate? Okay, so the moment pilot enters this data on this column, okay, though other data is already entered, taking inputs from the tower, okay, so there is a tower reported headwind. Now FMGC will compute the approach speed. So for computation approach speed, let us take 1/3 of headwind component. So VLS, how much it is right now? It is 131 knots. So 131 knots is your VLS. So I am writing this 131 as your VLS, okay, plus 1/3 of headwind component. So 1/3 of 8 knots, how much it is? It is coming to be 2 point something. Okay, so if we are considering 2 point something as 1/3 of the headwind component value and add with this, the value is coming smaller. So hence we prefer VLS plus 5 knots. So VLS plus 5 knots, how much it is coming? It is coming to be 136, right? So this 136 will be shown here. Okay, hence your approach speed is 136. Okay, and VLS is 131. So if you see 131 here, 131 VLS also will be calculated by the FAC, and it will also show 131 here. Okay, suppose 131 is here, so this VLS will be 131. Okay, so the VLS which is 131 here, it will FAC also will calculate it and it will come out to be 131. Okay, we'll also discuss the case if it's not 131, if it's some other value after some time. Okay, so hence what we have discussed here, VLS is computed by the FMGC and shown on the MCDU here, and for PFD it is here. Suppose the VLS on PFD is 131, this one, top of the VLS scale. Okay, and approach speed, you just check on the MCDU, just calculate by FMGC, is 136 in this case. So 136 here, where it will appear? Suppose here. Okay, so approach speed can also be seen on the PFD, and that is by means of a magenta color pointer. Okay, like this. I don't have magenta color pointer, friends, so I am using red ink to show you the approach speed. Okay, so this is represented by a magenta color pointer. So you can see that, friends, VLS is 131 and VAPP is 136. That means 5 knots difference is there. Okay, and here also you can see the difference between VLS and VAPP is 5 knots. So I mean to say, friends, FMGC always keep this much buffer between the VLS and VAPP, 5 knots. Okay, it is always a habit, you can say, of the FMGC to maintain 5 knots buffer between the VLS and the VAPP. Okay, that means the lowest selectable speed and the VAP will always have a difference of 5 knots or maybe more than this. Okay, depends on the winds reported by the tower. So suppose now, let's take another example. Suppose tower has reported wind component to be suppose 075 degrees. Now instead of 8 knots, they have said it is 45 knots. So now what is the 1/3 of 45? 1/3 of 45 comes to be 15, right? Because 3, so this is 45 and this is 1/3 of 45, this is 15, right? So it is coming 15. So now if I want to calculate VAP, so I mean to say whenever the wind is modified, the VAP also will change now. So VAP, how much it will be? It will be, I am writing it here, when winds have been modified. So VLS plus 1/3 of headwind component. So that is 15 knots. So VLS in this case is how much? 131. So it is 131 plus 15. How much is coming? 131 plus 15 is how much? 5 plus 1 6, 3 plus 1 4, 146 knots. So your VAP is 146 now. So accordingly this VAP also will be updated. Okay, so it will be 146. I mean to say whenever you change the data here or modify the data here, this also gets updated. Okay, approach speed. So this 146, you can see again this magenta color pointer will shift upward and it will show you 146. Okay friends, so I'm not drawing it here, okay, though it's understandable. Magenta color pointer will shift to 146 to show you this on the PFD. That is the approach speed which you see 146 on MCDU is indicated on PFD by means of magenta color pointer 146, where it will come somewhere around here. So here it will be the magenta color pointer. Okay friends, that's understandable. So I hope with these examples you have understood how do we have the approach speed computed by the FMGC. Okay, so the approach speed is computed by the FMGC based on these formulas. One thing which I forget to tell you friends is amongst these formula, this one and this one, okay, whichever is the highest, okay, that is considered as the final thing for calculation of approach speed by FMGC. Okay, so I'll write here. So whichever is the highest among these will be taken as the final value. So let me take another example. Suppose I am considering here, instead of this, the tower has reported the wind to be 075 degrees 6 knots. Okay, so 1/3 of 6 knots is how much? It is 2 knots. So it is coming 131 plus 2. I am getting the approach speed as 131 plus 2 will be how much? 133. Okay, and if I consider VLS plus 5 knots, it will come to 136. Okay, because VLS is 131. 131 plus 5 is 136. So which one should I consider? 133 or 136? So 136 should be considered. So I will not consider this case. Okay, so hence moral of the story, VLS plus 5 knots will always be the approach speed as long as your headwind component is less than 15 knots. Okay, why? Because when the headwind component is less than 15 knots, overall value for this VLS plus 1/3 of headwind component becomes lesser than VLS plus 5 knots. Hence, VLS plus 5 knots will always be the approach speed as long as the headwind component, that is the tower reported headwind component, is less than 15 knots. Okay friends? So I hope you have got how to calculate the approach speed and how to check it on the MCD approach page and on the PFD. Okay, now let's discuss an important case, okay, wherein the VLS indicated on the PFD is greater than the VLS indicated on the MCDU performance approach page. Okay, so let me quickly write this. In this case, how much will be the approach speed? Suppose I am considering these winds 075 degrees 06 knots. So in this case, 1/3 of this comes to be 2 knots. So in this case, the approach speed comes to be 136, right? Because it will be VLS plus 5 knots. It is 136. So this is your approach speed. This is your VLS. Okay. Now in this scenario, when you are having this data on the MCDU with approach speed being this and this, okay. In this scenario, if fact, because of some computation, it has calculated VLS to be suppose 133. Okay, so what happens is this 133 will be indicated here, right? VLS by means of the top of this amber strip. Suppose there is 133. Okay, so now if you see the VLS here and the VLS here, they are different, right? Here is 133 and here is 131. What about the approach speed? What about the final approach speed? That is VAPP. Here it's 136. Here also it is 136. Okay, suppose this is representing you is 136. By means of the magenta color pointer, I'm getting 136. Okay, so the top of this amber scale, okay, which I have told you in beginning, is your VLS. So VLS is 123. So friends, in this case you can see that the VLS and the V approach, how much they are having the difference over here. They are having a difference of VLS is your 133 and VAPP, which is shown by this magenta color pointer, it is 136. So it is a 3 knots. So now what I have told you that friends, we should always have a buffer of at least 5 knots between the VLS and the VAPP. And on the PFD we are not getting the thing. It's because of some computation it has changed the VLS. It has increased the VLS to 133. But on the MCD is the same. Okay, the 5 knots difference is there. But here on the PFD is not there. So what pilot can do is pilot can modify this VAPP. But how much to modify? So that depends on the difference between the VLS. So if you see the VLS in this case, which is computed by FAC, is 133. Okay, and here in this case is 131. So what you need to do is, okay, just check the difference between VLS indicated on PFD and VLS indicated on MCDU. How much is the difference? 2 knots, right? So 2 knots is the difference between VLS. So these 2 knots will be added to this approach speed, which is indicated here. So how much it will be, friends? Will be added by the pilot. So it comes to be 136 plus 2, 138. So pilot will modify the VAPP in this case. So this is the occasion which I was telling earlier, friends. Pilot can modify the approach speed, which is calculated by the system. So right now he is modifying, and how much he is entering? 138 knots. Okay, by entering on the scratch pad and pressing the line side key, 138 will move here, and that's how he modifies the approach speed. So now 138 is the approach speed. So in this case, this magenta color pointer will shift up. It was at 136, right? Now it will shift to 138. So when it shifts to 138, suppose it is shifting now, it has shifted up and it makes it 138. So now if I check the difference between VLS and VAPP, VLS is this one and VAPP is this one, how much it is? VLS is 133 and VAPP is 138. So difference is 5 knots now. So this is how we are getting the buffer of at least 5 knots between the VLS and the approach speed on PFD, and that we did by modifying the approach speed on the MCD performance page. Okay, and this was the occasion when pilot can modify the speed. How did we modify? The difference between the VLS of indicated on the PFD and this approach page, that difference we added to the approach speed whatever is written on this area. Okay, and then this approach speed gets updated. The magenta color pointer will be updated accordingly to show you the 5 knots buffer. Okay, so friends, I hope you have understood how VLS is calculated and how VAPP is calculated, and also how they are indicated. So that is how we have the VLS and V approach in this aircraft. Okay, so friends, let me quickly summarize whatever we have discussed. Okay, so we have discussed about the VLS and VAPP. VLS is the lowest minimum selectable speed and VAPP is the final approach speed, right? The purpose of VLS is to provide appropriate margin to the stall speed, and the purpose of final approach speed is to provide a stabilized approach. Okay, and that's by maintaining the approach speed. Okay, next, after that we have discussed where do we see the VLS and VAPP. Okay, so VLS can be indicated on the PFD, okay, and it can also be indicated on the MCDU performance approach page. So where do we see on the PFD? On the speed scale, there will be an amber strip. The top of the amber strip is what is your VLS. Okay, so this VLS is on the PFD is computed by FAC, right? How is it computing? By taking into consideration the aerodynamic data and the gross weight and CG. Based on the accuracy of calculation of gross weight and CG, the accuracy of VLS is also executed, okay, on PFD. Next, we also get approach speed here by means of a magenta color pointer, and this approach speed is calculated by FMGC. Okay, and the same approach speed is also indicated on the MCDU. Okay, next, what we have discussed on this amber strip, on the bottom part we have amber white, amber white, amber white, such type of strip. Okay, and this point, which on the scale it is the alpha prod speed. Okay, that is an angle of attack, which is called as alpha prod. And at that point of time, the speed of the aircraft is called as alpha prod speed. When the aircraft achieves an angle which is called as the alpha max, okay, that is when you pull the stick extreme aft whenever the high angle of attack protection is active. In that case, when the aircraft reaches alpha max, so this is the speed which aircraft will have. Okay, so this is the speed which is indicated on the PFD airspeed scale. Okay, so this is calculated by the FAC. Okay, FAC also calculate the characteristic speeds like the F speed, S speed, green dot speed, and the VLS. All these are calculated by the FAC. Okay, our main concern was with the VLS. Okay, so that's why we said VLS is calculated with the FAC based on the aerodynamic data in the CG and gross weight. Next, what about the VLS and VAPP indicated on the MCDU? So whatever we get on the MCDU, it is calculated by the FMGC. Okay, the flight management of the FMGC computes this, and we get it here. So suppose whatever wind you enter here, okay, so that wind has an impact on this VAPP, right? So we have seen some calculations. So we have seen that for calculation of the VAPP, FMGC uses this formula like VLS plus 5 knots or VLS plus 1/3 of headwind component. Amongst these two, whichever is the highest, and that is considered as the final approach speed by the FMGC. So we have taken example. Suppose we are having the wind. Suppose 075 degrees 06 knots is the wind information reported by the tower. We enter it here. So 1/3 of this 6 knots is coming to be 2 knots. So if I add this 2 knots to the VLS, because it is 1/3 of headwind component plus VLS. So in this place we are having 2 knots now and VLS here. So 131 plus 2 comes to be 133. And if we see the other part, it is VLS plus 5, that is 136. So amongst them 136 is higher, so 136 will be the approach speed, right? So approach speed 136 should be written. Right now it's not written here 136 because I have modified it. It is 136. Even pilot can also modify this approach speed, and that is applicable. Like one of the example I have taken, suppose what the VLS which is indicated on PFD is higher than the VLS which is indicated on the MCDU. Okay, it means because of some computation, if FAC calculates VLS higher than what is indicated on MCDU, then in that case the difference between the VLS indicated on the PFD and MCDU is taken, which is 2 knots in this example. Then that 2 knots is added to this 136 knots, and hence we get 138 knots. So pilot modifies this approach speed based on this now, and it comes to be 138 knots. Hence pilot can also modify the approach speed, which is though calculated by the FMGC earlier. Okay, so that's all what we have discussed till now. So this is how the VLS and VAPP are calculated and indicated in this aircraft. Okay, so friends, now let me tell you some important points about VLS. Okay, VLS information is inhibited from touchdown until 5 seconds after liftoff, and this VLS, which is computed by FAC, okay, it is how much? VLS will be equal to 1.13 VS1G, okay, in case of takeoff or following a touch and go. So it will be this much. Now this VLS, it becomes 1.23 VS1G whenever the flaps are retracted by 1 step, or in case of actual configuration the VLS is 1.23 VS1G. Okay, so this 1.23, which is, so this 1.23, basically this is applicable in case of all fly-by-wire aircraft. In case of other aircraft which are not fly-by-wire, that is the conventional aircraft, it will be 1.3 VS. Okay, next VLS can also become 1.28, okay, in case of clean config. So friends, VLS is 1.13 in case of takeoff or following a touch and go. Okay, and VLS is 1.23 whenever the flaps are retracted by 1 step. Okay, or in case of the actual configuration like during landing, okay, the VLS will be 1.23 VS1G. Okay, now what is this VS1G? VS1G is the stall speed at 1G. Okay friends, and VLS can become 1.28 in case of, sorry I forgot to write VS1G here. So VLS can become 1.28 VS1G in case of clean configuration. Okay, the next important point about VLS is above 20,000 feet, the VLS is corrected for mag effect to maintain a buffet margin of 0.2 G. Okay, and the other thing is, like whenever the speed breaks they are extended in flight, then also the VLS is increased. Okay, that is because the stall margin is reduced. Okay, hence the speed scale will show up whenever the speed breaks are extended. Okay, so I hope you are clear with this. I'll repeat again. So whenever the speed breaks are extended, the VLS is increased. Okay, VLS in config full, that is 1.23 vs 1g in config full is equivalent to your vref, that is the reference speed in case of normal final approach. Okay, that means the case in which you are preferring full flaps for landing. Okay, next thing, VLS is available in normal law also and in alternate law also. In normal law you will get this amber strip, and alternate law also you will get the amber strip. Difference between the strip indications in normal law and alternate law is that in normal law you get this alpha prot and alpha max strips, right? The amber strip, which is amber white, that is alpha prot speed, and alpha max, this you get in normal law. But in alternate law you lose these things, alpha prot speed and alpha max speed, and what you get instead of that, you get red type of scale which is along this speed tape, okay, or along this speed scale. Okay, and in that red color one indicates your stall warning speed, which is called as the VSW. So there will be a red color scale and this amber strip. Okay, so in alternate law you will have amber strip of VLS and the red black a barber pole type of scale, okay, which is representing your VSW, that is the stall warning speed. Okay, so that's in the alternate law. So friends, one more important thing, if pilot enters wrong information here, then FMGC also will calculate the wrong data here on this page. So that's why we have a second method of calculation, okay, or we can say Airbus have implemented a second method of calculation, which is this PFD for indication of the VLS. Okay, and that's what you have already studied, okay, indication of VLS on the PFD, right? If I talk about the limits of speed envelope, they are from VLS to Vmax, okay, which is this one, VLS and to Vmax. So these are all calculated by the FAC. So VLS is also calculated by the FAC and Vmax also is calculated by the FAC. Next, which is very important thing about VLS is, if suppose friends you have lost both the FACs, or if you have put off both the FACs, then all the characteristic speeds, okay, in which VLS is also there, okay, will be lost from this PFD. Okay, I'm going to say VLS will be lost if you have lost both the FACs. In that case, speed lim, okay, SPEDLIM flag, which is red in color, will appear here in this speed scale, and that indicates that you have lost the VLS also, okay, along with other characteristic speeds like your FS green dot speeds, okay, all those things also are lost when both FACs are lost. So hence, whenever you put off both the FACs or you lose both the FACs, that is these computers, you lose the VLS and other characteristic speeds from the PFD. Okay, the other thing friends, the VLS which is computed by FMGC and indicated on the MCDU, okay, this one like 131, that VLS is calculated by FMGC based on the zero fuel weight and the zero fuel weight CG, which is entered by the pilot in the MCDU. So it is the captain's responsibility to make sure that these data are correctly entered, okay, because based on this the VLS is calculated by the FMGC. So friends, I hope you have understood whatever we have discussed today. So I'll come up again with new topic in my next session. Till then, you enjoy learning this topic, and thank you.